Is everyone ready? Let's get ready for chemistry! I'm going to show you how to draw Lewis dot structures from simple molecules in this video. First, allow me to show you from start to finish, just straight through, how this process works, and then I'll go back and I'll break down each individual step by step, for you in exhaustive detail. So the first thing we need to do is to total the number of valence electrons. Nitrogen has 5 valence electrons. Oxygen has 6 valence electrons. There are 3 oxygens, so there are 18 valence electrons from the oxygen and 5 valence electrons from the nitrogen for a total of 23 valence electrons. Now, this molecule has a negative charge, which means it's gained an extra electron. So we're going to add that extra electron onto our total. So we have 24 valence electrons. Your structure must have exactly 24 electrons in it when you're done. The second step is to determine the central atom. The central atom is always the least electronegative, so nitrogen would be our central atom. And then we make a skeletal structure by giving each outside atom one bond to the central atom. So we start out by single bonding every one to the central atom. The third step is to give the outside atoms an octet. Since the bond is already a pair of electrons, the outside atoms only need another 6 electrons. We've given the outside atoms an octet. All of the outside atoms now have 8. It's time to worry about what the central atom is doing. Each oxygen has 8 electrons. There's 3 oxygens. We've used 24 electrons in our diagram so far. That means we have no electrons left over. But the nitrogen right now only has 6 electrons around it. It does not have an octet. But we're out of electrons to use. To get around this problem, all we need to do is share more electrons with the nitrogen. So one of these oxygens is going to share a pair of electrons with the nitrogen. So this pair of electrons becomes an extra shared pair of electrons, so we need to make a double bond. Please note that the oxygen is sharing an extra pair of electrons with the nitrogen. You are not just creating a new line out of nowhere. If you were to just make another bond instead of sharing that outside pair, then your total of electrons would be 26, and you can't do that. Because this is an ion, we would put square brackets around it, and we would put the charge in the upper right corner. Okay, let's go back and let's go over all of the rules one by one. Nitrogen has 5 valence electrons. All of the atoms in its column all have 5. Oxygen has 6 valence electrons. All of the atoms in his column all have 6. There are 3 oxygens for a total of 18. We're going to add on the 5 from the nitrogen, and we're going to add on the 1 extra electron from the charge. If this ion happened to have a positive charge, then we would be subtracting valence electrons. It sort of seems counterintuitive to be adding electrons when you have a negative sign, but remember that electrons have a negative charge. So the only way to have a negative charge is to be adding extra electrons. When we add these up, we end up with 24 valence electrons. That's step 1. The central atom is the least electronegative atom, usually. We've got some problems. Problem number 1, hydrogen can never be the central atom because hydrogen can only ever have 2 electrons around it. If hydrogen were to have more than 2 electrons around it, the universe would explode and we'd all die and it would be terrible, terrible burning death. So no more than 2 electrons around a hydrogen ever. Unfortunately, When you give hydrogen a bond, that's a shared pair of electrons. That's 2 electrons. So take home message here, hydrogen can never, ever, ever, ever be the central atom. Ever. So the central atom is the least electronegative atom usually. Pro tip, in a compound, the atoms are generally arranged in order of increasing electronegativity. So in this nitrate, the most electronegative atom comes at the end, and the least electronegative, I'm not going to write that word over again, the least electronegative atom comes at the start. So generally, the first atom in the compound is the central atom. So nitrogen would be our central atom in this case. Now, other considerations. Carbon, if there is a carbon in the molecule, is always to be treated as a central atom. If there are 2 carbons in the molecule, then they get to both be central atoms. But carbon is always, always, always a central atom, always. We'll give everyone 1 bond to the nitrogen to start out with. So that's step 2. Remember that the bond is a shared pair of electrons. So this oxygen already has 2 electrons around it. To give him an octet, he would need an additional 6 electrons. Now he has 2, 4, 6, 8 electrons around him. Now he has an octet. The other outside atoms need to have an octet as well. So we'll give all the outside atoms an octet, keeping in mind that hydrogen can only ever have 2 electrons around it. So once you give hydrogen a bond to the central atom, it cannot receive more unpaired electrons. We've used 24 electrons. There are none left. Step 4 is to put all of the remaining electrons on the central atom. Since there are no leftover electrons, we're going to skip step 4. Step 5. Check to see if the central atom has an octet. If the central atom does not have 8 electrons around it, we need to share extra electrons until it does. So we'll take a pair of electrons and we'll share it with the nitrogen. Bringing the nitrogen's total up to 8. Now the nitrogen has 2, 4, 6, 8. And this particular oxygen still has 2, 4, 6, 8. So everybody's got an octet. Everybody's happy. This is a stable molecule. But since it's an ion, we'll put square brackets around the whole thing, and then we'll put the charge in the upper right-hand corner. Let's draw a Lewis dot structure for silicon tetrafluoride. Step 1. Total the valence electrons. Silicon has 4, fluorine has 7, but there are 4 fluorines, bringing our total up to 28, plus the 4 from the silicon makes 32 valence electrons. We have 32 valence electrons to use and to work with. We want to determine who the least electronegative element is, so we can figure out who the central atom is. The central atom in this case is the silicon, because, oh my gosh, fluorine is the single most electronegative element, period. So it will probably never be the central atom. We'll give all of the outside atoms 1 bond to the silicon. Step 3. The outside atoms get an octet. Yay. Step 4. Check to see if there's any leftover electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I've used 32 electrons in my structure so far. I have no electrons left to use. So I will not be doing step 4. I will not put additional electrons on the central atom. Step 5. If the central atom has less than 8, it would need multiple bonds. In this case, the silicon already has 2, 4, 6, 8 electrons around it, so this is stable and there is no need to create double bonds. You only create double bonds if the central atom has less than 8 valence electrons around it. So this structure is good. There are no square brackets because it is not an ion. Let's draw a Lewis dot structure for xenon tetrafluoride. Step 1, total the number of valence electrons. The xenon has 8 valence electrons. The fluorine has 7 valence electrons. There are 4 fluorines. So 28 from the fluorines, and then the 8 from the xenon makes 36 valence electrons. The central atom would either be xenon or fluorine, but fluorine is always more electronegative, so we're probably going to go with xenon here. Xenon is the central atom, and by now you're probably wondering, why is a noble gas bonding at all? And as it turns out, fluorine is so electronegative that it can force xenon to bond with it. But who cares? We're just drawing Lewis dot structures. Xenon is the central atom. We'll give everyone one bond to the xenon. That's the 4 fluorines. The outside atoms get an octet. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. The outside atoms have an octet. I've used 32 electrons to make my structure. That means there are 4 leftover electrons. And where do those leftover electrons go? Step 4. Any extra electrons get dumped on the central atom in pairs. Step 5. Does the central atom have at least 8 electrons? Oh yeah, this particular xenon now has 12 electrons around it. It is definitely satisfied. It will not make a double bond. You have to have less than 8 electrons in order to make a double bond. So this is the Lewis dot structure for xenon tetrafluoride. It's got 4 fluorines, and the xenon has 2 extra lone pairs, 2 extra non-bonded electrons on it. Carbon disulfide. Carbon's got 4 valence electrons. Sulfur has 6, but there's 2 sulfurs for a total of 12. 12 plus the 4 from the carbon makes 16 valence electrons total. So we have 16 to work with. Carbon is always, always, always the central atom, always, except when it's not. So we'll give the 2 sulfurs a bond to the carbon. The outside atoms need an octet, so we'll give the outside atoms an octet. At this point, we've used 16 valence electrons, so there's none left over. So step 4, we checked it, and there's no need to do anything for step 4. Step 5, we need to make sure the central atom has an octet. Right now, the carbon only has 4 electrons around it. So we need to start sharing some additional electrons. We're going to share some non-bonded electrons on an outer atom with the central atom. That creates another bond. The carbon right now has 6 electrons around it. That's still less than 8. So what we'll do is we'll share another pair of electrons with the central atom. We'll just keep sharing until we get to 8. So this pair of electrons gets brought in to create a double bond. So now the carbon has 8 electrons around it, and everyone's got an octet, and we've used 16 valence electrons, and everyone's happy. So we would expect carbon disulfide to have a couple of double bonds in the molecule. Ooh, a molecule with hydrogen in it. Alright, let's do this. Phosphorus has 5 valence electrons. Hydrogen has 1 valence electron, but there's 3 hydrogens, so we would have 3 plus the 5 makes 8 valence electrons total. The central atom in this case is going to be phosphorus, because hydrogen can never ever be the central atom, because hydrogen can never ever have more than 2 electrons around it. So we'll give everyone 1 bond to the hydrogen, and then we'll give the outside atoms an octet. And we've used 24 electrons to... Oh! What happened here? We have negative 16 valence electrons to use. Something went terribly, terribly wrong. And the thing that went wrong is we put electrons on the outside of the hydrogen, which we can't do because the hydrogen does not get an octet. The hydrogen's orbitals are full at 2. So simply giving the hydrogen 1 bond to the phosphorus causes the hydrogen's orbitals to be filled up. So the hydrogen only ever gets 1 bond, and it never ever gets non-bonding electrons on it unless it's by itself. So we've used 6 electrons. That leaves 2 left over. Those 2 electrons go on the phosphorus in a pair. This then is the correct Lewis dot structure for phosphorus trihydride. You try it. See if you can determine the correct Lewis dot structure for hydrogen sulfide. Totaling the valence electrons, there's 1 times 2 is 2, plus the 6 from the sulfur makes 8 total. The central atom is the sulfur. We give everyone 1 bond to the sulfur. The hydrogens do not receive an octet because the hydrogens max out at 2. We've used 4 electrons in our structure. That leaves 4 left over. The extra electrons go on in pairs. Sulfur now has an octet, so we don't need to make any double bonds, which is actually good because if we needed to make double bonds, we wouldn't be able to because the hydrogens don't have any non-bonded electrons on them. Of course, that will never happen because of the way Lewis theory works out. Oh, let's try this one. Carbon has 4 valence electrons. Hydrogen is 1. 1 times 3 is 3. And then chlorine has 7. So 7 plus 3 is 10, plus 4 more is 14. This structure will have 14 valence electrons in it when we're done. No more, no less. Some people say that the central atom is the atom that there's only 1 of, but that doesn't always work. It's often the case, but it's not always. In this case, our choice is between carbon and chlorine, but carbon is always the central atom, always, so let's make carbon the central atom. We'll give everyone 1 bond to the central atom. Everyone gets 1 bond to the central atom. They don't get 1 bond to each other. They don't chain up, unless, of course, they do. But that's more complicated, and we'll talk about that later. So everyone gets 1 bond to the central atom. The outside atoms get an octet, but only chlorine because hydrogen maxed out at 2. We've used 14 electrons in our structure. There are none left over. The carbon has 8 electrons around it, so it does not need double bonds. So this is the correct structure for chloromethane. Why don't you try to get the correct Lewis dot structure for the phosphate ion here? Pause the video and see if you can come up with the right answer. The phosphorus has 5 electrons. The oxygen has 6. Times 4 electrons is 24 electrons plus the 5 from the phosphorus makes 29. But let's not forget about the 3 from the negative charge. So the negative 3 charge gives us an additional 3 electrons, bringing the total up to 32 electrons. This structure has 32 valence electrons to use. The central atom will be the phosphorus, Everyone gets one bond to the central atom. The outside atoms get an octet. At this point, we've used 8 times 4 electrons. We've used 32 electrons. There are none electrons left to use, so we do not put any extra electrons on the central atom. The phosphorus has 8 electrons around it, so it already has an octet, so it is stable. We'll put square brackets around it with the charge in the upper right corner because it's an ion. Pause the video and try to solve the correct Lewis dot structure for the chlorate ion here. Chlorine has 7 valence electrons. Oxygen is 6, but there's 4 oxygens. 6 times 4 is 24, plus the 7 from the chlorine makes 31. And if you total up the valence electrons and you end up with an odd number, you should try and do your math over. Just double or triple check it, because electrons like to be paired up. And the only reason for making a molecule is to make the atoms more stable as a molecule than they are by themselves. So if it doesn't have an even number, it's probably not going to be a stable molecule. There are, of course, exceptions to this, because there's exceptions to everything in chemistry whenever you try to come up with a rule. But in general, you shouldn't have an odd number. You should have an even number of valence electrons. What we've forgotten here is that the ion has a charge of -1, so there's an extra valence electron, bringing our total up to 32, which is an even number, which makes us feel good about ourselves. Chlorine is the central atom. The outside atoms get one bond to the central atom. The outside atoms get an octet. I've used 32 electrons. There are none left over. The central atom has 8 electrons around it, so it is stable, and there is no need to make double bonds. But it's an ion, so we'll put square brackets around it, and then we'll put the charge in the upper right-hand corner. Last one. Pause the video and try to solve the carbonate ion for its correct Lewis dot structure. Follow the rules and follow them in order. Carbon has 4 valence electrons. Oxygen has 6. 6 times 3 is 18, plus the 4 from the carbon makes 22, plus the 2 more from the charge makes 24 valence electrons. So we have 24 valence electrons. The central atom is the carbon. The outside atoms, the other atoms get one bond to the carbon. The outside atoms get an octet. At this point, we've used 24 electrons. There are none left over. There are no more electrons to put on the central atom. The carbon right now only has 6 electrons around it. So it needs to have an octet. It needs a double bond. Sharing an extra pair of electrons with the carbon brings our total up to 8. This makes the molecule stable.
Is everyone ready? Let's get ready for chemistry! Yeah, 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 yeah.